Hello, and welcome to Generative AI in Business, an outlook for the next 3 to 5 years of AI tech. You can go to the next slide. I'm Casey Brandt, a standards coordinator for Conexus, and your moderator for today is David Ezell, the director of new initiatives at Conexus. So if you'll move on. The agenda for today, I've got a few quick things to go through before we get started. We're going to go through some housekeeping things, a little bit about Conexus, and David's going to introduce the presenter, and then it'll go on with the presentation. And then afterwards, we'll have a Q&A session. So make sure you get your questions in as soon as you can, so that way the sooner they're asked, the sooner they can be answered. Can you move on? Thank you. So a little bit of housekeeping. The replay will be made available on conexus365.org. You can send your questions in, like I said, through the Zoom interface. And PCI credits are available for qualifying live events, so please contact us if you're interested in that. Next slide. So this is just a disclaimer, a slide our lawyers make us put in. Basically, the views and opinions are solely of the speakers and not of Conexus itself. Move on. All right, so a huge thank you and shout out to our 2023 annual sponsors at Conexus. The extra support is really appreciated and allows us to continue the work that we do on behalf of the industry. All right, so a little bit about Conexus. So Conexus is a nonprofit technology organization. Our members really do the heavy lifting here. So we provide a neutral forum where retailers and vendors can network, come together, and create standards and solutions that are beneficial to our industry. We educate through white papers and events like this at Conexus 365, and we advocate on a technical level at other organizations to help steer the conversation around standards and policies so that changes don't negatively affect your business. You can move on. And for a little bit of information about Conexus 365, there's an educational webinar series. We have monthly webinars, so make sure you're subscribed to our email list and you check out the website to be notified of future webinars. We'll be having a think tank session on November 30th, and our quarterly Connect with Conexus event will be next in December on the 7th. So make sure you contact us, mention on LinkedIn. You can look for conexus.org. All right, and you can now I'll turn it over to David Ezell to introduce our speaker for this webinar event. David?
All right, hello everybody, and thanks for coming to our webinar. It's my serious pleasure to reintroduce Dr. Alan Lockett. And Alan spoke for us at the annual strategy conference, and his specialty is, I'll just say, applied AI, which is, for a lot of us, really the only way we can understand it or use it is when somebody helps explain it to us. So Alan's background is as an AI entrepreneur working in the commercial space, specializing in natural language and text. He went to college at University of Texas at Austin, where he earned his PhD. And I won't tell you all of the topics, nonlinear optimization and that sort of thing, but these topics in his thesis were published as a book after that. He also got an NSF, National Science Foundation grant to study in Switzerland robotic perception in action. So he kind of covers the gamut of the AI space, and also knows an awful lot, which is what he's going to be talking to us about today, about how to put things together and make things work. We will be taking questions. There is a way you can pose questions. I'll be watching those. And I see that we have at least one serious AI expert on the call, so I really sort of expect I'm going to see a question from you, and you know who you are. So anyway, with that, I will, and I will probably wait on the questions until the end of the presentation. But if something seems really timely, Alan, I might interrupt you if it seems like it's a quick hit. So anyway, with that, Alan, take it away.
All right. So let's see, get this all working. There we go. So the topic is generative AI in business. The goals today for our presentation are to understand what's available today in a commercial sense, to explore how we can apply those to solve technical problems and business problems, and then to look a little bit at what the future capabilities of AI look like. And we'll end with some sort of attempt to think about the sort of further future, but we've got quite a bit to go through, so let's go ahead and get started. I wanted to start off just going over a bit of the history of these systems and where they came from. To start with, if you look at what we can do with these systems today, and these are things that you could do using commercial tools today, you can have a conversation with AI about really any topic you want. You can translate into almost any language that's written down, except some very rare ones. You can see an example of translating into Thai there on the left of your screen. These systems can ace professional exams. We see that they've passed the bar exams, they've passed medical exams, and so on. You can generate images from text. You see an example of a sunrise on Io, or a school teacher lecturing her elementary students on the right, both generated by a tool called Midjourney. And then they can analyze textual content. So, for example, I asked it to analyze a quote there on the left, and it gives sort of a literary analysis of it. You could summarize complex text, retrieve information from large data sets using semantic cues to find information. You can answer questions about data, generate software code, transcribe human voices into text. You can have it vocalize text and sound like a human. You could clone a human voice. You can copy a human image and make video. You can generate natural audio from text as well. Like you could say, okay, well, give me a sound of some birds chirping, and there's software that will do it. So what are the limits then, given there are all these capabilities now that have suddenly sprang onto the scene in the last couple of years that weren't here before? Well, some of the problems come from the way these systems are. One of the main ones that people talk about is this idea of hallucination. AI essentially is trained on a large set of data, and it imagines the average outcome, if you will, over its training data, and makes up information, so-called information, to fill the gaps in its knowledge. For example, I've asked it before to tell me about a war fought between ancient Rome and China. And it gave me generals, places, dates, and of course, none of this ever happened. The two empires did not have that kind of contact. So it makes up stuff. These systems are highly intelligent, capable of answering very complex problems, but they aren't particularly insightful. If the information isn't already in the data somewhere, where the data somewhere means everything on the internet and practically everything ever written by humans, it's not necessarily going to invent it. These systems are not necessarily inventing new things. And so if your goal is to have these systems tell you what the molecular definition of the next new cancer drug is, they're going to struggle to tell you that. But if you ask them what cancer drugs people are working on that show promise, it could certainly help you out. There's also a problem of expense. These systems basically take a supercomputing cluster at this stage. They run on GPU hardware at scale, making it very expensive. And for now, at least, the hardware is somewhat hard to get a hold of because the demand has spiked through the roof. This means that depending on your application, you may or may not experience scaling problems. If you want to analyze, for example, billions of documents, it's going to prove difficult to find the resources. There are limited applications still in audio and video, particularly around generating video or understanding video. It's lagging behind because video content has such high bandwidth and is difficult to analyze for that reason. But these areas are under research. Audio is a bit further along than video, but still lagging behind where we are with text and images. And I would say one of the other limits is this idea of disembodiment, that because AIs live in the computers for now, they have limited tools to test or check assertions. They don't get external feedback from this thing we call reality, which might feed back into the hallucination problem above. So these are some of the limits and some of the problems. Of course, if you use the systems, you'll encounter the limits that are relevant to you very quickly. So just a very quick little bit of history. It was way back in the 1700s, 18th century, when it was discovered that electricity actually moved the muscles. Eventually, the source of that electricity was found to be in the brain. And by the late 1890s, Ramon y Cajal had started to map out and make these beautiful pictures of neurons, giving us an understanding of the structure of how the basic fundamental unit of the brain works. You can see over to the right an image of a neuron. It has this central body, the soma, and then these dendrites that gather information from sometimes tens of thousands or more of other neurons so that it can detect what's happening in the brain around it. And then it gathers up those signals, and if there's enough signal, it will fire or activate, sending an electric potential through its axon out to the synapses on the other side, which then in turn connect to other neurons. This sort of circuit pattern inspired the creation of the digital computer in the 1930s and 40s. People like Alan Turing and John von Neumann were inspired by this idea of how brains work to build the basic architecture of the digital computer. Efforts to build artificial brains started around the 1940s. We have in 1943 the McCulloch-Pitts model. They proposed something called the perceptron, which looks a little bit, not exactly, but a little bit like the diagram on the bottom right, where you see that the dendrites are modeled by these arrows, and you can see that each dendrite, if you will, is more or less sensitive to what came before it. So we attach to each input a weight that indicates the sensitivity of the artificial neuron to the incoming neuron, so that when the incoming neuron fires, then that weight is used to modulate the amount of input coming in. Those are summed up, and based on how high or low they are, the neuron will either emit an output signal or not. We use a nonlinear activation function to prevent it from sending any information when the inputs are low, and to send more information when the inputs are high. That's the basic structure of an artificial neural network. It was worked out how to train more than one of these things in a chain over the course of the 1970s and 80s. The biggest discovery there was an algorithm called backpropagation. And what backpropagation does is it says, well, we're going to require our nonlinear function to be differentiable, and then we can apply calculus, and then we can have a network of these things, and we can start at the output side and simply propagate errors backwards, and then we can tell each weight how it needs to adjust itself to do a better job on some task. And so these large systems of neurons are then trained to optimize for a certain task by shifting their weights a little bit at a time, so that these things are trained incrementally over millions of steps, in some cases billions or trillions of steps today. So the core challenge here, and you can see there was a development of these things. Of course, we had convolutional networks coming in for images over the course of the last decade. But the key events actually was the development of sufficient computational power to handle these large systems. It was in 2011, 2012, when the first GPU-trained networks came online. They were used in 2012 to solve a task of recognizing thousands of different kinds of objects in millions of images in a problem called, the network was called ImageNet. And so moving from there, now the neural networks, deep neural networks, became powerful enough to solve real problems. When I was in undergrad and even graduate school in the 1990s and 2000s, people said neural networks will never solve a real problem. They aren't powerful enough. You need to use other techniques. Well, the problem was they just weren't big enough, and we couldn't handle networks that could solve these problems. And that's the trend that keeps moving forward. So what is it that makes AI successful now? I mentioned the computational issue, that we just didn't have computers big enough, but there were other issues. For example, within academics, there was a lot of resistance to the simplicity of the neural network idea. It wasn't as exciting, for one thing, to talk about millions upon millions of very simple artificial neurons interacting together. There were also some problems within the math where it wasn't clear how these systems would work, whether they would work, why they would work. And the idea of proposing to spend millions of dollars building these systems when you didn't have any solid mathematical proof that they would all work out in the end made it difficult to commit the resources for experimentation. And in a lot of ways, Hinton's lab up in Toronto, and then later Ilya Sutskever at OpenAI, are responsible for making these multi-million-dollar bets that these large enough systems would work out. And those bets I think we all see, been quite successful up to this date. Another major discovery along the way, specifically to the natural language capabilities, is something called the transformer architecture. It is today applied to image problems, video problems, action problems, robotics, and so on, in addition to natural language. But this is the one that really made natural language possible. I'm not going to dive too much into the architecture, but I will say that whereas the simple neural networks that we talked about before have those just chains of those simple neurons, transformer architectures have something additional called an attention mechanism that lets it connect up different neurons in different ways depending on the input. This is what we would call a second order network within AI. And so this second order algorithm then has significantly more power than a basic neural network. That was discovered in 2017. And another issue is that the general capabilities of large language models were just really unexpected. So let's talk a little bit about large language models. What do I mean? The basic task for a large language model, and there are variants, is this idea of next word prediction. So the way this works is if I give the network some input, such as the quick brown fox jumped, then I ask the network to predict what the next word will be. And there are several words that it could be. The standard natural language processing sentence has over as the next word, so that's maybe the highest probability. But you could imagine jumped down, jumped into. There are probably a dozen different words that equally make sense with over. But still, it's not all of the millions of words in the English language. There's a limit to what could come next. So there's something for the network to learn. So what we do is we take a huge text corpus and we just ask a neural network, a very large neural network, to learn to predict what the next word will be. And it will be wrong many times because the next word could have been many different things. But in the main, there is a pattern to which words come next, and these models will learn that pattern. Well, now, once we've learned to predict what the next word will be, we wind up with some interesting consequences. And this is what people really weren't expecting, but it became apparent in around 2019 that this was what was happening. That text completion is what we now would call a master task. And what I mean by that is if you look at many different tasks, you can phrase them in such a way that they become text completion. You suppose you want to answer questions. Well, so I ask, what is the capital of Hawaii? Well, if I complete that text, the text is likely to have something about Honolulu in it. If I could do the same thing with translation. If I say, the dog translates to French as, well, I expect the next two words to be le chien. And for summarization, if I say, this is a summary of War and Peace, then I might expect, well, a social exploration of Russian society in the wake of Napoleon's invasion in 1812 or something of that nature. The idea is that once you can predict the next word, if you can do it well enough, then you can convert that next word prediction task into very many useful tasks. Now, when we talk about language modeling, this has some roots in statistical modeling. Language modeling typically means next word prediction. So predicting the next word is all that means. Now, what do we mean by large? Quite large indeed. If you were to look at GPT-3, which came out, I believe in I'm not even going to try, it's around 21. But it had 175 billion parameters. And the size of that network, these are 32-bit floating points, that's 700 gigabytes worth of data that makes up all of the different weights of GPT-3. More recently, Meta Research put out Llama 2 and announced that it was trained on 1 trillion tokens of data. That's how much training data. So what you have now is lots of weights, very many parameters, lots of training data. And what we found is that there seems to be almost no limit. If you add more of both, more parameters and training data, things just tend to get smarter and smarter. The limit, of course, is your pocketbook, which is not infinite anywhere. It now costs tens to hundreds of millions of dollars to train some of the very largest models like GPT-4. Now, how do we measure how well a language model is doing at predicting the next word? This is called perplexity. Perplexity is basically the odds of getting the next word right. Back in 2017, the best model would get 1 in 40 words right. By 2022, the best models are getting 1 in 2 or 3 words right. Now, this is on a task of predicting the next word in a subset of Wikipedia. And Retro was a model put out by Google DeepMind. On some more difficult tasks, if you look at things like GPT, GPT-2 got 1 in 20 words right. GPT 3.5, 1 in 4.6, GPT-4, 1 in 3.5. Now, less than 25% chance of guessing the next word correctly may not sound like much, but the problem is the reason that's a good thing is that when you look at the words that actually are predicted, they're very, very likely and very good alternatives to the first one. And so these things can basically speak English now. Now, that's not enough in the end. You actually need more than that because these things are trained on all of the internet, including Reddit. And when you are in a business context and want to, say, write a document for your superiors, you don't necessarily want it completed to sound like it's on Reddit. The way that we deal with that is by introducing some post-training. So we train the network with next word prediction, that's phase 1, and then we apply a series of techniques to make it behave better. This is called reinforcement learning with human feedback. The way that things like GPT 3 and 4 are trained is that the second phase is a supervised fine-tuning phase. So we get a bunch of instructions, a bunch of dialogues, things that we would like to see the network produce, not just things out on the internet, but stuff that we want it to do. And we train it a little more to focus in on the things that we want to see. And the final phase is human preference tuning, where we go out and we now ask the model some questions, and these models, they're stochastic. They don't always generate the same text. So you can generate different texts by simply querying the model multiple times. And so we generate 3 or 4 texts, say, put them in front of real humans who then go and rank the 3 or 4 texts that we gave them. This one's the best, this one's next best, this one's the last. And then we train what's called a reward model to judge the statements so that it matches human judgments. And then now it can judge the network's output. We then use that reward model to optimize the network further, which gives us then the final output of a GPT-4, which is trained to output text that humans will like. So now that we know what these things are and how they're trained, let's talk about solving problems with them. The way you use a large language model is by putting in a sequence of text. And as I was discussing with the master task idea, you can use this to solve question answering problems, translation, summary, code generation, and so on. For something like a GPT-4, the way this looks is you give a prompt that describes what you're asking the network to do, and then you can iterate. Then it iterates back and forth between the human giving input and the machine giving a response. Prompt engineering is a term that refers to describing and instructing the neural network with human language. This is a new area. So the idea now is that if you figure out how to talk to these machines, then they'll do your tasks better. And there are people that specialize in this, and there's an art to how you set up your problem and explain your problem. This isn't like software engineering because it's wordsmithing. You are setting up an English text. So this is how we're going to solve problems with GPT. Here is an example of solving a SQL task with GPT-4 using just their public interface. If you get an account and look at their playground, then you can do this. This is using ChatGPT version 4. On the left, I have the system message. This is the first thing that is given to GPT-4, and it is considered the most important by GPT-4, so that GPT-4 will emphasize paying attention to the system message. So I told it, you are a data translator that takes English statements and transforms them into SQL queries. The user makes a statement, you provide only the query with no commentary. Questions by the user pertain to the table. I give it a table for employees. And then all responses should be formulated to query this table. That's my system message. That's my instruction to GPT-4 of what the task is. So then I come over as the user and I say, list all employees with surnames starting with A, and it then issues the SQL, select star from employees where last name like A %, which is then going to look up all the employees that start with a capital A. And then I ask it how many employees started between two dates with a salary less than $100,000, and then it can look up employee counts based on the hire date and the salary. And then I can ask even more abstract questions like list all employees who are paid more than their manager, and it will do the proper join. Now, you could imagine, rather than giving the SQL as a reply, you could then run those replies through the actual database and instead respond with numbers. So now you can use a large language model to ask questions of your data in a way that lets you mostly operate without a specialist who knows how to read and write SQL. So this should be a great democratizing power for allowing all of us humans to interact better with computers. So that's a little bit of the kinds of tasks you can solve. Now, large language models don't just run on words. Instead, they break up words into tokens that are chosen to efficiently encode the text. It's kind of like a Huffman encoding for those of you who know what that means. So here I have some text. In a hole in the ground, there lived a hobbit. And I've separated it into tokens for specifically for Mosaic ML's MPT. But you can see these pipes indicate where the token boundaries are, and you can see that there's roughly the common words are each a token, but then when you have a longer or less common word like hobbit, it gets broken up into two tokens, hob and bit. And also the period and the comma are tokens because these machines don't just take text, they take whatever bytes you want to feed into them. And they can, for that reason, they can read software code. They could even read more complex formats, although they may or may not be trained to handle them, like image formats or PDF formats or whatever. So these are tokens, and tokens are important because essentially they're how you get charged in a lot of these systems, and they're also how the limits are determined. So to talk a little bit about the limits, I mentioned the transformer architecture. It developed out of machine translation, where you needed these attention mechanisms in order to figure out word order. For example, in English, the adjective comes first. In French, the adjective comes after the noun. So figuring out when to translate each word was handled via these attention mechanisms. And eventually someone realized that these attention mechanisms were powerful enough to stand on their own. They made an entire neural network out of these attentions, interspersed with some traditional neural networks, and that was called the transformer architecture, and it has had a major impact. The thing about attention is, in order to apply this attention, you're connecting up, you're trying to decide which elements in a sequence are going to be relevant for predicting the next word. And when you do that, you can only look at so many elements. There's a limit to how much information you can consider. You have a maximum number of tokens that we call the context length. And this remains true when you move over to a commercial application and want to use a large language model. There's only so much that it can pay attention to. So these context windows typically range from about 2048 to 8192. If you're wondering why there's such odd numbers, those are powers of 2, which are very important in computers where you have binary codes. But the longest available context length is about 65,000 tokens. That's with Anthropic, their Claude 2. The enterprise version of GPT-4 typically takes 8,192, but they have a version that will take 32,768 tokens. And that's the limit of how much these systems can see and how much they can use to reason over things. So now, what if you have more than that? that. So what does more than that mean? Firstly, it means about 20 to 50 pages of text, depending on the prompt, depending on the particular model you're using. Each token's roughly a couple words, so 250 words per page means 500 tokens per page. So if you're going to have 4,096 tokens, like say Llama 2, that allows you to put in about 8 pages of text. If you're going to use the biggest version of GPT-4, then that will allow you to put in about 65 pages of text. Now, 65 pages sounds like a lot, but suppose you want to query, for example, the entire US legal code, or all SEC filings, or the entire corpus of English literature. In that case, you're going to have to choose a smaller set of information to send to the LLM. And so then you need to figure out, how do you pick that smaller set? So now I have this diagram here. You might have a query that's going against a knowledge base. Then you're going to feed that, some subset of that knowledge base into the LLM to get your response. Let's talk a little bit more about that. But first, we have to talk about vectors. So large language models process the input, which is a sequence of text. And for each time step, it will it transforms the token that comes in into a sequence of numbers. So here I have one token and represented by one box, and then 4 boxes here on the vertical representing 4 different numbers. In reality, these systems typically have something like 4,096 or 12,000 up to 16,000 elements in these vectors. But for each token, I get a vector that represents, essentially projects that token into the space that we might think of as a space of meaning that the large language model uses to reason. And things that mean similar things are going to end up in similar spaces, in this similar places in this large vector space. So now, if I have a representation in this large vector space, so you can think of it like a whiteboard where you write, you write dog here, and then you write canine nearby. So the things that mean similar things end up in similar places, and you can test what's close together. Well, I can have a list of documents here, a list of searchable list of documents, and I can go and I can transform them all with a large language model into vectors. And then I can store those vectors inside a vector knowledge base. Now, when I have a text query, then I can pass it through my large language model, get out that vector, and then compare it to all the vectors in my knowledge base to find the matching documents out of my search set. So and this is a semantic match, not a keyword match. So if I search dog, something that has canine could well come back. And so this is a vector database. It's a new way of searching that is a bit more semantic, and it lets us find relevant text in a large corpus of text. And I have scaled these things up to the capability of searching billions of vectors on a single large GPU machine. If you don't have a large GPU machine, then the scale is somewhat smaller. But what I really want to talk about is how this plays into applications of AI. This process, so there is a process called retrieval augmented generation. This is a form of AI search where we have a text query. We run that query against a database. Now, that could be a SQL database. It could be a keyword query with an inverted index. It could be a vector database. But the point is, the result is a set of matching documents, which we can then feed into a large language model with a long context window and say something like, here is some information, list off all the documents, and then say, given only this information, respond to the following query, give it a text query, and then read off the response. Retrieval augmented generation is really useful for limiting hallucinations, because when you do this, you're essentially telling the machine the kinds of information you want it to take into account, and the machine does a pretty good job of limiting its responses to the things that you've provided it. This also lets you include large bodies of information. It lets you get under the context length. And you should notice now that what we're starting to do is to assemble generative pipelines. For one thing, the vector database that you use over on the left-hand side does not have to be the same as the large language model you use on the right. And in fact, cheaper and smaller large language models have been found to be useful for this RAG process, so that you can reduce your costs in processing by using a smaller model on the left and then a larger model on the right to still get high quality generation. So as we move through how to use these things in practice, here's another idea. This is called chain of thought reasoning. The problem is that when you just use an LLM, it will often make mistakes that are reasoning mistakes. So for example, you see on the left of the image on the right, Roger has 5 tennis balls, blah, 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 and then he ends up with 11 tennis balls at the end. And then there's another question about a cafeteria and how many apples it has. And if you just prompt the machine, it will give you the wrong answer. But looking at the rightmost panel, if instead you demonstrate how to answer these word problems by going through a variety of steps, then the model will also go through the steps. And in this case, it gets the right answer because now the sub-steps are there inside of its reasoning. All the stuff that's highlighted in green is available to the model when it needs to declare that the answer is 9. And so on the original paper a couple years ago that did this, they were able to use PaLM, which was one of Google's large language models, to increase the percentage of math word problems answered correctly from 18% to 57%. And people have expanded on this idea. There are ways of making it generic or more abstract. For example, you can ask the large language model to formulate a goal and then formulate sub-steps and then perform each sub-step and then return the answer. And you can sort of hold its hand and lead it through this like you're working with a sort of an idiot savant, if you will. Another capability that these large language models have is generating code. And what that means is that you could not only have them generate code, but you could run the code they generate. So for example, just to highlight one, ChatGPT now has plugins that you can upload, and GPT models will generate function calls to execute against these plugins. So you can do things like, well, they have it limited in a variety of ways, but in theory, you could do things like send emails or schedule meetings and so on. So what you're looking at now is a number of different capabilities provided by large language models that can be strung together in a new kind of modular programming. Now, what's different about this is instead of stringing things together with just computer code, you can now string them together with English. You can speak to the machine and tell it what to do. You can provide a set of standing instructions for it to perform. And that's what I mentioned AutoGPT in the other slide, or I put it on the other slide. That's one of the things that AutoGPT does. So there are several ways to invoke LLMs. You can ask them a direct question or ask them to complete some text. You can perform an AI search with retrieval augmented generation. You can call external functions, generate images, generate code. You can, with GPT-4, for example, and with others of the newer breed of not just language models anymore, you can prompt them with images, which they are then able to analyze. Each of these then can become modules in a new type of program. We can then assemble graphs of large language model actions or AI actions and tie them together with software, making a chain of behaviors. And so one of the packages that does that is LangChain. I've got a little bit about that below. Those are some of the things that you can do with large language models. So now let's talk about commercial off-the-shelf solutions. What is out there? Well, there are a number of these large language models that are available for use. The one that everyone has heard of is, of course, ChatGPT, but most of the large companies have their own offerings. Microsoft is partnered with OpenAI on ChatGPT, but Google has a range of things. The newest one is called Gemini. I believe it's either has come out or is coming out soon. Amazon has Titan. Anthropic has Claude. One that I haven't worked with is AI21 Studios has one called Jurassic 2 that's supposed to be good. All of these offer API access. They run the supercomputing cluster for you, but they also keep the model and you don't get to see what's inside it. So if you have high privacy concerns, you have to work at it. I do know that, for example, OpenAI, if you talk to them, and I think maybe now even in the intake forms, you can specify that you don't want your data saved, but you have to be cognizant of that as a possibility. and make sure that you're covered with respect to privacy and security in a number of applications. So sometimes proprietary models won't work for you. Well, now there's increasingly good open source options. They haven't fully matured. So the proprietary options are still better than the open source options as of October 2023. But particularly with the recent release of Meta's Llama 2, they're catching up. I know that Falcon recently released a 180 billion parameter model I haven't had the chance to work with yet. There's a few others that are not as well developed, such as Mosaic ML's MPT. And one of the first ones in this area was Bloom. But increasingly, what I expect is that we'll see better and better offerings in the open source domain. And the nice thing about these open source models is you can customize them to do whatever you want. And then, of course, there are people who will build you proprietary models that are specifically yours. These are some small companies. I haven't worked with any of them directly, but I'm sure that not only these, but many others are out there and will be out there. So we'll see how that all develops. Now, if you're going to try to run these open source models, then you have to have AI hardware. Where are you going to get it? You can, of course, go to the major cloud providers. The problem there is that they do not offer in their standard offerings the most recent hardware, but they still have good hardware and they have good procedures and they integrate very well with everything else that you need. Their prices are also a good bit higher, though, sometimes double for what you get versus specific AI cloud providers. So, you can go to Amazon AWS or Microsoft Azure or Google Cloud and get resources. There is increasingly sort of a middle tier of more specifically AI cloud providers. They don't necessarily provide everything that you would need in a cloud, but they do provide AI hardware. These would be places like CoreWeave or Lambda Labs. Mosaic is very nice because they also offer a lot of pre-baked solutions for using large language models. So they can connect you with both compute and with the algorithms and tools that you need to have these things, to build these things very quickly. So Mosaic, they've got a tool called Inference that lets you run inference on these large AI models, Mosaic Inference. And so there are the cloud solutions. If you won't need to or have to run your own hardware, then at this stage, you're pretty much only going to NVIDIA. The A100s is the generation before last, and now the current generation, the H100 chips, those are the cutting edge standard right now in 2023, and they're hard to get. But AMD and Intel also have options, and thanks to things like OpenAI's Triton, some of this will be more and more available and useful for people. Commercial off-the-shelf vector databases. Two companies to call out would be Pinecone.io and Zilliz. I'm sure there are probably others because this is a very new area, but I'm sure there are others that are going to come in. But Pinecone is built off of an open source tool called Face. You can just use Face directly for a small problem on a single machine. If you have large problems or need commercial availability guarantees, Pinecone.io is an option. Zilliz is built on a different vector database called Milvus. Both of them are high availability, fast response. The prices are not cheap, though. It's cheaper to run your own, but then you have to build and maintain the infrastructure. I do want to mention LangChain. LangChain provides Python, JavaScript libraries to invoke chains of large language model behavior. So this lets you implement sort of that modular control flow. It's a very neat little tool. So they provide standard classes for interacting with third-party models. You still have to go and get the account with those third parties to integrate it in, but they provide software glue. They have primitives for retrieval augmented generation, preset templates of different chains for things that you might want to do, like summarization or translation. They have this concept of agents that sort of take standing orders and execute them. So you give them English language standing orders, sort of. And then they also have integrated callbacks that let you log and monitor the steps as things walk through these chains. And there's tons of examples. It's a great place to go and see the kinds of things that you might do, even if you're not interested in using that tool. One other thing about this, sometimes you're going to want voice-to-voice conversation with an AI instead of just text-to-text. This is very doable. You just break it, but you go from speech to text and then text to speech, and in the middle, you use these LLMs. And there are a variety of different solutions that are available, both on the speech to text and on the text to speech side. The text to speech side is a little bit less well developed. There's some of the newer methods are just coming out, but there's still several options, several good options, some of which I've listed there. In terms of pricing, usually you are going to pay per token. For example, it was 3 cents per 1,000 tokens for GPT for the 32K context window in this month. I think it's 1.5 cents per 1,000 tokens for the 8,000 context window. All of these companies will do enterprise agreements with you. A lot of the newer ones, like 11 Labs, which does voicing, and Pico Voice provides a whole lot of tools in the ecosystem around a large language model. A lot of these want subscription fees, in some cases very large subscription fees, in order to let you use their services. And then there's usually a pay per unit fee once you get past a certain limit. Vector databases like Pinecone.io charge based on how many databases you have and how big they are. At scale, it could make sense. If you're a very big multinational, it could make sense to use open source models and homegrown infrastructure. But when you talk about that kind of scale, you're talking about billions of tokens, billions of documents, the scale that would let you buy, a few thousand GPUs. So for almost every project that any of us would work on, including at large multinationals, it's simplest to start with these API-based tools and subscriptions or usage charges and see how far you get before thinking about how to scale up. Now, I am aware that it is 11:46. I'm going to go very quickly through the remaining slides here and then open us up for questions. So I'm just going to hit the highlights. You could ask an LLM or an AI. We should use a more general term because these things will handle not just text, but images, audio, and video very quickly here. You could answer questions based on a corpus. You could summarize a passage, comment on proposed communications, like you have a press release and you want to ask what angle, you have a variety of angles or different personas, and you want to ask how they would react to this press release. Then you could ask GPT-4 and get those different perspectives. You could use these things for customer service, inbound sales, as a receptionist, an interactive out of office message, say. There's a number of different things that you could do. Some of the things to think about when you think about where is this all going to go in the future? Well, in 3 to 5 years, we're unlikely to be anywhere that isn't already under development in research labs today. So if you want to know what's going to happen in 5 years, it's usually enough to ask what's being developed in the research labs today. And we should expect to see an acceleration of existing trends. We can already see this modular programming using LLMs coming in. That's going to become more defined, more usable, and more accessible to people over time. There's the trend of open source versus multinationals, the multinational corporations, so that the proprietary models from the open AIs and such. This will play out probably in the same way that operating systems did in the 1980s, 1990s. We'll see the open source over time become better and better. And of course, because they're cheaper, then more people will prefer to use them. There is one wild card, though, and that's the expense of training these models. It's a lot cheaper to build an operating system than to train a large language model. So we'll see how that all develops, but I think the open source will become more and more robust over time and more desirable. Of course, the hardware and its availability is a big issue and a big limiting factor right now. I don't think that's going to resolve anytime soon. So you have to think about how, what sorts of certain scales of application are going to be more feasible than others, simply due to the limits on hardware. Even if you have the money, it just increases the price. And we will see regulation. It's not clear exactly what form this will take. In many ways, we're already, the horse is already out of the barn for a lot of that. Some high-level predictions. Natural language interfaces will become the de facto standard for interacting with computers. This will be true within 5 years, not longer. And it'll be the standard and the norm within 10 years. Now that you can talk to a computer, people will expect to be able to talk to a computer to talk to their data and so on. You can expect to see more and more multimodal systems. GPT-4 already handles image and text. There's a system out of Microsoft that was released this summer, handles text, image, audio, video as input or output within the same model. This is just going to continue, and gradually these systems will be multi-capable and multifunctional. I already talked about the demand bottleneck on hardware, but AI will be everywhere. By 2030, it will be harder than it is now to get a human on the phone, although the robot on the other side will be more capable. And this is going to have positive and negative implications in our society. It'll be interesting to see how those interact. I don't want to opine too much on that. But the big question is, how does it impact your business if people can talk to computers, if computers can translate data into English, and if computers can talk to each other in English? Think about all the things that makes possible. One other trend just to mention is this idea of personalized AI. Right now, we have these big proprietary models like ChatGPT, but eventually you'll want a personal assistant that's your personal assistant, that's on your team, and this will develop over time. It may sound like a small thing, but remember, the personal computer was dismissed as kind of silly in the 1970s, but we all know how important that ended up being. Similar things will happen with AI. So ultimately, AI right now is like computing in the 1970s. Remember when everyone used mainframes? Everybody kept paper files. Computers were used by large companies, and corporate leaders were convinced that the businesses were basically going to be fundamentally the same moving into the future. IBM was at the top of the heap and poised to stay there. And places like Microsoft and Apple, Google, Facebook, none of them existed. This is where we are with AI today, and so it'll be pretty exciting to see how all this develops. And that's it. Questions?
Thank you very much, Alan. I have so many questions myself, but I'm going to hold those. I have one from our audience. Thanks for a great presentation. Microsoft 365's November release will include Copilot based on OpenAI's ChatGPT tech, I think for $30 a month per user. What is your expectation on how this will enrich and empower the regular user for AI? And I think regular user means developer in this case.
So the first disclaimer is that there's so much going on in this space that I cannot possibly keep up with every offering that every company has. Microsoft, I've seen some very interesting things that they're talking about doing. I'm not sure exactly how much they've released. So as for Copilot, I pay for Copilot. So I pay that $30 every month to use Copilot. The reason I do is because where I used to have to copy paste code and then alter parts, now I can just have it predict for me what I'm about to write. Only the variables are already changed correctly. And or if I want to write a function, all I have to do is write the documentation for it, and then the code will pop in. It will mostly be wrong, but if I wasn't already sure exactly how it was going to do it, I can analyze it and say, oh, well, that seems like a good idea. And a lot of times it'll recommend libraries I didn't know existed. And so then I'll just make a library call instead of rewriting something that someone else has already done. So it's extraordinarily useful. People like Lex Friedman has said that it makes them 100% more effective. I don't know about that, but I'd certainly own 10 to 20% more effective than I was before. So very useful, and I do highly recommend it.
I want to add one thing, which is you talk a lot about LangChain, and I've seen that in operation, and it's very amazingly easy to use, and you can instruct it things in English. But if you have Copilot running in your Visual Studio Code, it will actually suggest the rest of the sentence that you need to put in the prompt for the AI.
Yep.
which
Oh,
is
there was a paper about this. I can't remember the details. It was like last week or something, but someone basically said, okay, well, look, the way to handle these things is suppose, so you want to make an image. Well, make a prompt and then ask an LLM to make it a better prompt.
Yeah, and it works. I've seen it. Okay, let's see. Here's another one. Do you think we will be headed toward a future of distributed computing, for example, blockchain over hosted computing to handle increased processing demand?
I don't know. So right now, one of the big, so if I understand the question is basically, okay, so you have, first you make the observation that you have a ton of computing that you have to do, and that these models take a massive amount of computing. So why can't you distribute that computing? And then maybe my computer isn't big enough to compute one of these large language models, but between me and the 10,000 other people that aren't always using our computers to their full capacity, we could negotiate together and have those computers act as a supercomputing cluster. It's an interesting idea. Will it happen? I don't know. Right now, the problem is the really large, really good models are so huge. They're running on specialized hardware, and really without that specialized hardware, you cannot train these things. There's a lot of people who are very good at getting these 32-bit weights down to like even 4 bits, and people are running some moderately large models on a single machine. I think that potentially the algorithms themselves will change. Potentially our ability to use the algorithms more efficiently will improve. There are tools like LoRa, low rank adaptation, and Clora, quantized low rank adaptation, that allow these things to run on smaller and smaller hardware. The latency introduced by processing blockchain in the middle might make that a difficult proposition, but perhaps it'll happen. I don't know.
Okay, so here is the question that always comes up. Legal implications. What are the risks of using cloud-based LLMs in the RAG process? Is there any sort of risk to your proprietary information, or are there ways to mitigate that?
So I happen to know a little bit about the legal tech industry, having worked in it for several years. And there are, there are lots of people who have concerns and lots of people who don't. And it's sort of up to you whether you want the lawyer who has those concerns or the lawyer who doesn't. And it may turn out to matter quite a good deal to you later in a courtroom, which one you chose. But I will say that many cases are already running in the cloud in places like AWS or inside of Azure. And a lot of sensitive data is put into these systems. They have procedures that they say makes them secure. I have also heard people argue that nothing is really all that secure when you've got a key somewhere that somebody might happen to get a hold of that would let them not only see their own data, but the data of others. And then there's the question of what about the personnel at AWS? To which my response is then, okay, so you're a large law firm, and you're going to have a whole bunch of computers on premise at your site because you believe that's more secure, but then you're going to hire IT people. And in a sense, they're a part of your firm, but in another sense, how much loyalty do they have to you really? And how vulnerable is your information really? So my tendency would be to say nothing is ever secure. Now, back to the AI part of the question. When these companies like OpenAI sign an agreement saying they won't use your data, how confident are you that they'll respect that agreement? Well, I'd be fairly confident because they've got a lot of money at stake. But how much do I trust them to set up? If you're not going to negotiate them, you're just going to put your stuff there. I'm sure they would use it to train something, right? If you don't proactively make sure that your things are secure and that you have negotiated agreements that cover you, then you will be vulnerable. And how much will it matter? Well, if they use your information to train a system and then somebody else asks the right question, they can get your information back verbatim. There are, of course, several lawsuits pending currently against OpenAI for sucking in the internet and using it to train GPT-4. And we'll just have to see how that plays out in the courts. but I would say that the question is a quite valid one. And I don't have the resolution to it. And we're going to see this play out in the courts and in politics and in business over the course of the next few decades.
Well, and with that, I believe we are at the end of our hour. Thank you so much, Alan. Speaking for myself, I'd like to see us do a semi-annual update on this technology, because it's going to be moving so rapidly, and new things that are hard today are going to become very easy, as you've already warned me. So thank you very much. And Casey, do you have closing for the meeting?
Sure. So just like David, thank you, Alan. Thank you, David, for speaking to us today. If you have any questions that you didn't get to ask or didn't get answered, please feel free to reach out to us. We'll reach out to Alan to get some answers for you. And also make sure you tune into the next webinar that's going to be on November 30th. Thanks. Have a good week.